Hi. So, we are going to start with some calculations regarding the intensity of a wave, either a sound wave or a light wave or any other wave that is emitted from a particular source. The first calculation is going to be for uh, a wave that emits from a source with a certain rate of energy transfer, which is, of course, a power. So, let's say that we have a light bulb here, and it's emitting at 60 watts. And we want to know how bright the light bulb is at a distance of 3 meters away. So we'll make this 3 sig figs. So all we would have to do is calculate the intensity of that. So the intensity is the brightness of light or the loudness of sound, essentially. We'll come back to that in a moment. And the way we'd calculate that is the power of the source divided by 4 pi, and then you divide also by the distance away you are from the source squared. And the reason for that is the total rate at which the source is putting out energy, which is the power, is being spread across a whole spherical shell of a radius r. And if you remember, the surface area of a sphere is 4 pi r squared. So if you can imagine that power being smeared across that entire surface, then the amount that you get at one little point is divided by that entire surface area. And as this spreads farther and farther out, it gets smeared out over a larger area if you are farther distance out. So in this case, we have 60.0 watts divided by 4 pi r squared. Get out a handy dandy calculator, and our r, we said here, was 3.00 meters squared. And so we have 6, 5, 4 pi 3 squared. We're just squaring the 3, and we get 0.0531. And the units are watts per meter squared. And so that's telling you that for every square meter that you have, if you imagine a window with 1 meter by 1 meter side, that there's a total power of 0.0531 watts passing through that window at any given time. The other calculation we have here is we don't necessarily know the power in the middle of a particular source, but we do have the intensity at one given point, and we want to calculate the intensity at another given point. So the idea is, sure, there's a source in the middle, but what we have is the intensity here, so we could call that I1, and we have R1, but we might want intensity 2 at a distance of R2. So let's say we have intensity 1 equals, I don't know, 1.25 watts per meter squared, and this distance R1 is 2.00 meters, and we are at a distance twice as far out. So R2 is equal to 4.00 meters. Now we don't really need to do a calculation. If we look at this equation, we see that the intensity drops off as the square of the distance. So if we are twice as far out, the 1 over r gets squared. Hopefully that's still recording. Sorry if it blacked out for a second. So if we double the distance, that 2 gets squared, and so we have a 4. But let's say we just want to complete the calculation anyway. So we want to solve for I2 here. So we have 1 over I1, and we have R2 over R1 squared. We're trying to solve for I2. So we have I1 times R1 over R2 squared equals I2. And we can plug in our numbers here. So 1.25 watts per meter squared times 2.00 meters over 4.00 meters squared. Of course, I picked a number that does not divide by 4. Terribly easy. But 2 over 4 quantity squared. I guess it's not that bad. 3.1, and then if we use right sig figs, we get that. Okay, so that is how you calculate intensity from a source, or how intensity scales from 2 different distances from the center where the source is.